Welcome to Study Loop.
Hello everyone, today we're doing chapter 17, problem 60, and this problem gives us this molecule and asks us three questions. In A, it asks us what type of orbitals does a lone pair on each nitrogen atom on this heterocycle here reside in. B asks us to explain why the bicyclic ring system that contains both nitrogen atoms is aromatic, and C asks us to draw the resonance structures of this bicyclic ring structure. So let's start with A, determining the molecular orbitals that each of these lone pair on each nitrogen atom exists on. So we know that nitrogen has lone pair electrons, but we also know that in terms of aromaticity, only atoms that are, or only only electrons that are located in these p orbitals that are going up and down can be delocalized and involved in determining aromaticity. If there's any orbitals that are going within the plane of your carbon-carbon bond, like your s orbital or another p orbital, another type of p orbital, then these are not able to be delocalized around your ring, so they cannot be included in aromaticity. Something else that we know is that for heteroatoms, if you have a double bond on a heteroatom, we know that its lone pair is going to exist in this p orbital that is in the same plane of carbon-carbon bond, so it's not involved in determining aromaticity. So because of that, we know that this nitrogen has 1, 2, 3 things attached to it. So we know it's an sp, s to the power 1, so we need 2 more things to equal a total of 3. So we have an sp2 nitrogen here. So this nitrogen exists, this lone pair on this nitrogen exists on an sp2 carbon. Well, what about this nitrogen here? Well, this nitrogen, it has those 3 bonds that are all on the plane of the carbon-carbon bond. But now we have this lone pair that is actually on this p orbital that is going up and down, so it actually be involved in delocalization. So because of that, here, what we have here is now an sp2 carbon, sorry, an sp2 nitrogen, but now these electrons are located in the p orbital that can be now delocalized and determined and be contributing for determining aromaticity. B asks us, why is the bicyclic ring that contains nitrogen, both nitrogens, aromatic? Well, we know that aromatic rule has to follow the 4n plus 2 rule. And we know that because these 2 electrons on this nitrogen are in the p orbital that can be delocalized, they're involved in determining aromaticity for the number of pi electrons. So we know that we have 2 pi electrons on each of these alkene bonds, so that's 4. We have 2 more on this nitrogen atom, so that's 6. We have a total of 6 pi electrons. So this does follow the 4n plus 2 rule of aromaticity with n equal to 1. So we have 4 times 1 plus 2 equals those 6 pi electrons. So yes, this molecule is aromatic. Why? Because this nitrogen's lone pair electrons are in the p orbital that is going up and down, so it can delocalize within the ring. However, this lone pair electron of this nitrogen is in the sp orbital, so it cannot delocalize around the ring. C asks us to draw resonance structures for this bicyclical ring structure. So let's redraw the molecule actually, or the bicyclic ring. So we have a double bond nitrogen here, double bond here, go up to a nitrogen up here, and then these groups go off to be something else. So we have 2 lone pair electrons. So let's use this nitrogen's lone pair electrons to delocalize around the ring. So we make a bond. When you make a bond, you break a bond. So this 2 electrons here can now go on this nitrogen atom. So now what we have here is, oh, sorry, let me redraw this. Now what we have here is nitrogen now with 2 lone pair electrons, which is negatively charged, which actually isn't all that favorable. So what's going to happen is that one of these lone pairs is now going to continue going through the ring, to make a new bond. When we make a bond, you break a bond. And now we form this molecule here. And now nitrogen has 4 bonds, giving it a positive charge. And then once again, these 2 electrons can go back onto nitrogen's nucleus to regain our very first molecule here.